Let's begin the first session of today. We had a wonderful, splendid yesterday actually, and really happy to continue it today. The first speaker is Rajesh Gopakumar, and he will talk about driving the simplest gauge string duality. I told him that he's my friend, but he's not going to get any extra time.
So, firstly, birthday wishes again to you, Hiroshi, and also thanks to all the organizers, particularly Mazenc, for bringing us all together to celebrate this nice occasion. Yesterday, Spenta showed these pictures of Hiroshi at his first meeting in IIT Kanpur in 1987. Actually, but for what you might call a small thermal fluctuation, our world lines might have intersected, and I would have joined Spenta in being the person to have known Hiroshi the longest in this gathering. So I was actually a first-year undergraduate student in 1987 at IIT Kanpur, and I had heard of this exciting string theory meeting that was going to happen. Of course, I didn't know anything about the subject then, but there was the buzz about string theory, and I very much wanted to attend it. But then it was during the winter break, and the semester was over, and it was my first North Indian winter, which can be very harsh without heating. So I decided in the end to miss it. So in that sense, it was a thermal fluctuation that moved our trajectories away. But in any case, our world lines intersected again. I think Hiroshi may not remember, but I was a graduate student in 1996 attending the TASI lectures in Gonda. And I was hugely impressed by his lectures for their clarity, their insight, and particularly the aesthetic blackboard work, which was just like printing it on the blackboard. And of course, since in the years afterwards in my physics universe, Hiroshi has sort of grown much more to influence my science, and of course lately even institution building and so on. So so this work today that I'm going to talk about is a sort of a bit of a drastic condensation of some ongoing work with Edward Mazenc, who is here, a terrific young postdoc from Chicago. So this is going to come in 3 installments at some point. I mean, for an occasion like this, I think the best present one can give someone like Hiroshi is to offer something, ideas, themes which are very close to his heart, and to which he has, in fact, very strongly influenced. So it's in that spirit that I offer this talk. By the way, this is a picture of Hiroshi literally reaching to the stars in the planetarium in Bangalore. The Indian premiere of this film that that yesterday you also heard about. So Hiroshi came for our 10th anniversary, and this was one of the highlights. It was a packed auditorium, and this is Hiroshi greeting the mother-in-law of the current UK Prime Minister. So in any case, okay, so let me, like a Japanese gift, sort of unwrap it in sort of layers for Hiroshi. First, I'll sort of just make a sort of proposal for what I would like to call the simplest gauge string duality. And then I'll argue explicitly that you can check this duality. You can actually check correlators arbitrary correlators at all genus and see an agreement. You can argue for the agreement. But the more interesting question for me is, why is there this agreement? And how can you sort of make it manifest or sort of structurally exhibit the reason for this agreement? And that's one of the things we've, I think, gone some way towards answering. And finally, I'll try to sort of embed this in the bigger picture of gauge string dualities. So, so what I call so in some sense, very arguably the simplest large N theory is just that of a single matrix integral, n by n matrix, and single trace correlators, correlators of single trace operators. Of course, this appeared yesterday in the talks of Steve Schenker and Jan, and I must emphasize that here they play a very different role. I'm not going to be employing these matrices to understand the fine level statistics, but view them more as sort of open string degrees of freedom, and how you can how they transmute into a closed string description. So why is this the simplest? Because in some sense it captures all the Wick contractions of free theory and the free Toft expansion. All the combinatorics are in a sense captured by a correlator like this. Moreover, you can generalize it to an interacting model, so an arbitrary potential in this classic paper, and then you can take the double scaling limit. And in the 90s, one understood a lot about the string theory in such a limit. But here I do not want to take a double scaling limit, but talk about the dual string description of just the simple integral itself, and in principle with a perturbation to an arbitrary potential. So, so this I'd like to argue is sort of a stripped down to the essentials version of gauge string duality. And you can see the Gaussian is sort of the analog of the tensionless limit, and then you can perturb away from it as well. And as I said, the main question for me is whether if we can propose a sensible dual, whether we can make the equality of correlators manifest. We can derive it in some way, as we've made some headway in a similar way to the headway we've made in tensionless limits of ADS3 most completely, and beginning to do so in ADS5. So that's the sort of the goal. So this is the proposal, just in case you miss on all some of the details later, but this is sort of the one takeaway message, that the Gaussian matrix model correlators there's a sort of two closed string duals. One is a model topological string theory on a familiar geometry, a cigar-like geometry, which is a Kazama-Suzuki model, a twisted C equal to a twisted C hat equal to 3 Kazama-Suzuki model as with the SL2R at level 1, and with, very importantly, a certain deformation of it, a certain momentum background, which I will talk about later. And the claim is physical correlators in this are the same as of these, and there's a mirror version of this, which was known before. It's a Landau-Ginzburg theory. So there's a B-model description, the Landau-Ginzburg theory with a superpotential, which is sort of 1 over Z plus Z. And again, the claim is that correlators of physical observables in this theory agree with those of the Gaussian matrix model for arbitrary genus or arbitrary endpoint function. So L's are integers. So the claim is that this is true. So first, as I said, I'll try to argue how why this is true. I mean, not why this is true. How you can check that this is true. The statement. So this is the equality I was claiming. So the way to argue for the equality goes through some auxiliary chain of theories which are probably familiar to people who were around in the 90s, because a lot of this work was done mostly in the 90s and early 2000s, especially in this corner here. So the idea is that we will be able to map this matrix correlator to another sort of a matrix model, which arose, it goes by different names, that arose in the context of the C equal to 1 string theory at self-dual radius. which and so this is a mapping we will be able to very explicitly carry out. And it was well known that you can, that this matrix model captures the scattering amplitudes of this C equal to 1 string theory. We will be considering the case with a deformation or a sort of a tachyon background. And this, so once you have this, then you know that there's another chain of reasoning which tells you that this is equivalent to this A-model theory, and there's a mirror symmetry to this B-model description, or equivalently, this is also related to a B-model on the deformed conifold, and therefore connects with similar ideas of digraph and buffer. So this is sort of, so I'll flesh this out a little bit. So firstly, let me look at this part of the equality. So this is a map between two different matrix models. It's something you can just, it's an equality of matrix integrals. The most transparent way to see this is to start with something, a two matrix integral of this kind, involving an arbitrary potential and some source terms. And you can rewrite this using sort of a Hubbard-Stratonovich type of trick in terms of a different. So if you start with an n by n matrix, two matrix integral, you can write it in terms of a q by q matrix integral, a different matrix integral of the somewhat different looking potential. And in fact, we will consider, we'll actually need not the most general form of this equality, which is something it's a topology, but we'll look at a special case where this is just Gaussian to begin with, and we'll set some of these sources to 0. So when you do that, actually this two matrix integral just becomes a one matrix integral, a Gaussian with a generating function of traces, of powers of traces, and that's the same as this equality tells you that that's the same as a somewhat different looking model. It's actually closer to a Kontsevich type matrix integral, again with a source term. So this x's are sources for these t bars are sort of the sources for these arbitrary traces, trace m to the k, and in this description, those enter into this source matrix X over here. But you see that in this description, there's a sort of a logarithmic potential or a Penna type potential. So there is a physical interpretation for this equality of matrix correlators. In some sense, if you wish, these describe open string degrees of freedom of sort of compact branes in the ultimate geometry that we'll have, and these some non-compact branes. In the special cases of the double scaling limit, these corresponded to certain branes of Liouville theory. And there's a more general description of these in terms of the graphs. They the Feynman graphs as sort of an interchange of graphs and dual graphs. That's what this equality boils down to. But this matrix integral, this Kontsevich type matrix integral, was well known to describe the C equal to 1 string theory at self-dual radius. And we will be considering the case with a sort of a quadratic deformation of that theory. So the theory without this, with this T2 set to 0, would have been the one that described the C equal to 1 string theory at self-dual radius. But we turn on a certain fixed background, mu, which is sort of related to n. And this captures this S matrix of C equal to 1 string theory of negative momentum tachyons. So these sources here correspond to, or the x's here, the t bars correspond to the negative momentum tachyons, and the t's correspond to the positive momentum tachyons. So you turn on only a positive momentum with momentum 2 in this the self-dual radius, and this so this captures the Gaussian correlators, and this is an exact expression. It's true for true genus by genus, and of course we did some sanity checks, and in fact it was sort of satisfying for me that a calculation I had done as a graduate student 27 years ago, which I didn't understand the reason. So there, I mean, so at that time with Sunil Mukhi, we had observed that the 1-point function of a Gaussian is the same as what you get from the C=1 string theory. But now we understand the reason why that actually agrees, and more generally, not just for a 1-point function, but for arbitrary functions. But you can explicitly check, and we did some sanity checks to make sure that we weren't missing anything. So
you turn on only momentum, no 1D?
No, only momentum, yeah. So I was sort of indicating this chain over here, and once you have this chain, then everything else sort of follows, and I don't have the time to describe the details, but essentially the C=1 string theory, which is sort of a Liouville plus matter field, can be mapped to this A-model background because there's a sort of a Wakimoto representation of the cigar geometry, and that plays the role of the Liouville, and then there's the extra cigar direction, the circle direction, and so these two can be mapped, and this is sort of well known, and there's a mirror symmetry that relates this to the Landau-Ginzburg theory, and people actually, and including people here in the audience, sort of looked at the connection to the C=1 string theory, etc. So I don't want to belabor the point over here, but just to say that through this sort of duality chains, you can explicitly check that these are the equality between correlators here and correlators in this in these two theories. So but the goal here is to sort of short circuit this. So I use this sort of indirect way to kind of argue for the equality of these two things, which you can then, of course, check. And but doesn't tell you why these are the sort of the natural closed string duals to these to this Gaussian matrix model. And so that's what we would like to sort of derive. And I'll try to indicate how that goes. So there are two pictures, the B-model and the A-model. So we'll look at each of them in turn. So what does it mean to try to derive this duality? So one halfway point is to start with the matrix model expressions and rewrite them as integrals over moduli space, because that's sort of what a string correlator would be like. And then you can look at the integrand on moduli space and try to understand that, the kind of worldsheet description, the worldsheet string theory corresponding to the integrand. So here, let me first focus on the halfway point about, and there are two natural ways in which you can start with the Gaussian model and try to rewrite it as integrals over moduli space. So on the B-model side, associated with the Gaussian matrix model is a spectral curve, which is a Riemann surface, and which is parametrized in this way. It's a you can see it's just a quadratic Riemann. It's a quadratic equation between x and y. In fact, it's the complexified version of the Wigner semicircle distribution. So that's the spectral curve associated to this matrix model. And there's been this whole machinery of topological recursion relations, which are probably familiar to some people in the audience from the recent developments in the of Sarge, Schenker, Stanford, and in general in the SYK model. But so this machinery of topological recursion, which again I don't have time to go into, it gives you an algorithmic way of generating these correlators in terms of correlators at arbitrary genus, in terms of some these traces, if you expand them, you get these correlators, there's these are encoded in certain differentials, which there's a recursion relation, that's the topological recursion relation. And one of the crucial ingredients is the number of branch points of this spectral curve. And you can see here, with this parameterization here, you can see that and that there are two branch points for this Gaussian matrix model spectral curve, and that will be important for what we'll have to say. So this work of Eynard and others, they went on from the topological recursion relations to actually to write down an expression for these generating functions or these differentials as integrals over moduli space in a very generic way. And I'll say some of this in the next slide. But so this machinery gives you a recipe to rewrite the correlators or the generating function of correlators in terms of integrals over moduli space. So that takes us sort of to this halfway point. So that's the B-model picture. There's at first sight, a different way in which the moduli space arises from the A-model side. And that relies on another old observation about the correlators in a matrix model, which actually I think goes back to Isaacson, that these combinatorially account for certain what these numbers are counting. These are just some pure numbers from the Wick contraction. What they're counting is a set of holomorphic covering maps of a certain kind from the genus G world sheet with n punctures to a target space B1, which is in some sense related to the spectral curve. But in any case, so the purely combinatorial interpretation of the Feynman diagrams in terms of vertices, edges, and faces, there's a beautiful relation to covering maps of degree, which the sum of all the L's, and having exactly 3 branch points with very special branching profiles at these points. So the 3 branch points at infinity, if you wish, there's a branching profile L1, L2 up to Ln. And at 1, another point, it's just a simple branching, and there are L by 2 of those. So in some sense, these correspond to the vertices of the Feynman graphs. These correspond to the propagators, the big contractions. And then there's one which corresponds to the faces. So there are 3 branch points which correspond to vertices, edges, and faces. And the product of these is identity. So once you specify these 2 permutations, the third one kind of gets fixed. So in any case, these special covering maps that you can associate to this Gaussian matrix model also have a very nice interpretation in terms of moduli space. They correspond to very special, you can think of them as coming from very special lattice points on moduli space. The ones which are parametrized, those who know this terminology, they are the ones for which the Strebel differentials have integer length or positive integer length. So these are very special points on the moduli space. So that's one way in which the A model, also the Gaussian matrix model correlators, can be written in terms of certain quantities on moduli space. Okay, so, but what about these? How can you connect these integrals on moduli space with the sort of B-model theory that I was proposing? In the B-model, it's this Landau-Ginzburg-like theory. Well, you start with these expressions of that topological recursion gives you, and you can actually make a correspondence between. So these are the operators. Trace M to the L are related to certain operators on moduli space, which are given in terms of the so-called psi classes on moduli space, which appeared in the work of Kontsevich. And so these are integrals over moduli space which generalize Kontsevich's original intersection numbers. So there's a very explicit operator dictionary that you can make between these single trace operators and these psi classes on moduli space. All these coefficients can be very explicitly written down. And there's a background. So the Gaussian potential corresponds to another very specific background that you can write down in terms of classes on the moduli space. But this integral is actually not over the moduli space as such. It's actually over something at first sight a little unfamiliar. It's over two copies of the moduli space. And these are associated to the two branch points that I mentioned that the spectral curve has. But actually, once this has a very natural interpretation in terms of the target space that we are proposing here, because this Landau-Ginzburg superpotential has two critical points, which are, because you see the spectral curve is the same as the spectral curve that appeared in the matrix model. And there are the same two critical points. And in the B model, you have just constant maps from this, from the world sheet to these critical points. And these, in a sense, capture precisely those contributions. So one way to interpret these results of Eynard is that what you get are 2D topological gravity correlators after you've integrated out the matter fields of the Landau-Ginzburg theory, because this B-model theory is a theory with these matter fields coupled to two-dimensional gravity. But once you've integrated them out, you get contributions just from, so the only remnant of this is the fact that there are these two copies of moduli space that enter, because in a sense, that's what the space of maps reduces to. You can also view the solutions of topological recursion as the Landau-Ginzburg matter integral. There's a way to write it, which connects with things that people did with Landau-Ginzburg theory. There's also an interesting connection which we haven't fleshed out, which is related to the Cordera-Spencer theory on the spectral curve and an interpretation of the topological recursion relations as Schwinger-Dyson equations for the Cordera-Spencer theory. And that's related, at least it's not, it's related more to the deformed conifold story, the Digraph-Buffer story, which is not exactly the same as this, but I think very closely related. So in the B model, you can see how the target space sort of emerges from the matrix model. I mentioned in the A model that there was this other way in which you got this localization on special points in the moduli space. The first thing I want you to notice is that, or I want to just bring to your attention is that these special points, I mentioned these lattice points, this sort of localization happened also in the recent discussions of the tensionless limit of ADS3 strings, because in that context, it followed from the fact that the SL2R worldsheet theory that describes ADS3 with 1 unit of NSNS flux. So this was something Hiroshi and Juan taught us how to study this. There are spectrally flowed vertex operators in the physical theory, and you have to be very careful in studying their correlators when you consider the special limit, and you get only contributions from moduli space which admit holomorphic covering maps to P1 that specify branching. So this is something we had seen, and it was very crucial to make the connection to the symmetric orbifold theory in that context. But here, so something very similar happens, because you see the Kazama-Suzuki theory here is also at level 1, and that's very crucial for it to be at the critical central charge. And the physical vertex operators are in the spectrally flowed representation. So precisely the operators corresponding to these in this Kazama-Suzuki model are in the Lth spectrally flowed representation with at the bottom of the continuum, or the discrete representations with J equal to half of SL2R. And so the same arguments that we had in the case of ADS3 apply here, and you have the similar holomorphic covering maps, but there's no space-time dependence now because these are purely topological. And so the branching is all at infinity, which is sort of at the compactified cigar end. But the deformation that I told you of with the momentum 2 tachyon, those are in the background, and for momentum conservation, you have to pull down as many of these terms in the background to sort of conserve the momentum. And so you get precisely branching from of this 2 to the L by 2 which I told you was the branching you had corresponding to the propagators of the matrix integral. And then there's the Liouville interactions, which in some sense capture the third branching point. So this, I think, gives a kind of a, I think there are still details here we are trying to nail down, but I think the broad picture that emerges is very consistent with everything we know for ADS3 as well. So before I conclude in my last couple of minutes, I just want to, you might be wondering how this has to do with the double scaling limit. In both these pictures, you can sort of recover the observables of pure 2D gravity. So what you see in the double scaling limit by going to a sort of a BMN-like limit, namely by taking the taking operators with very large operators, trace m to the l, with L becoming very large. And then when you look at the expression that I showed you earlier, it simplifies in this limit, and you get precisely the Kontsevich type of integrals that correspond to the pure gravity and the pure 2D gravity case without all the matter. So it's in this BMN limit that you see the full moduli space emerging, because now these, and you see that very explicitly in the A model picture, because these discrete volumes go over to the continuum volumes, because you sort of densely cover the moduli space. And in fact, this is very similar to the mechanism of the large twist limit of symmetric product CFTs in the limit, in the tensionless limit of ADS3. So I think this is satisfying that you sort of see how you recover the continuum moduli space from these very from these discrete points. So in my last minute, I'll just sort of embed this in the bigger picture. I think that, and one of the reasons I think this is interesting, apart from its intrinsic interest as a toy model for the string duality, is that there's a precise embedding of this subsector, I think, in the full ADS CFT holography. And I think there's a sort of a chain, an inclusion chain, if you wish, where this, on the open string side, if you wish, the Gaussian matrix model is a subsector of what's called the chiral algebra sector of the n equal to 4 Yang-Mills, which are protected sector, but with chiral holomorphic dependence on correlators. So this is, here the correlators are pure numbers. There's no dependence on position. Here there's a holomorphic dependence. And of course, here you have the full-fledged n equal to 4 Yang-Mills. And there's a closed string embedding, I think, of this as well, with the, at least in the B model picture, you see the B model with this superpotential that I argued. It's very close to the deformed conifold, and probably you can show that it's exactly equivalent. And this is a subset, if you wish, of the B model on the SL2C that has been recently proposed as the dual to the chiral algebra sector, the so-called twisted holography. And this, I think, makes the relations to the tensionless ADS3 CFT2 limit also sort of more natural. Why is it that we were seeing so many of the features of the tensionless limit of ADS3 CFT2 in this very simple case? And then, of course, these sit inside the big duality, but I think if we, by understanding this subsector very well, I think it will enable one to get a very fine-grained understanding of holography here, at least in the tensionless limit. And perhaps, as we saw in the Gaussian case, you can perturb away from the Gaussian, so hopefully you can carry out the analogous procedures here. So happy to take questions. I hope Hiroshi is not too puzzled by this, and you'll be happy with any answers that I can give. So happy birthday again, and many years of wonderful research.
Yeah, so thank you very much for your kind words. Remind me of nice memory from India. So So I have a question about tensionless limit. So there have been quite a bit of discussion on exactly what the tensionless limit in this type of description, in particular, for example, if you take a SL2R model, what the precisely the value of K to be. So here you
At
say
level
K,
one.
level one, and
Level
the
one.
reason is
That's that's in the ADS3 case, that's the smallest volume, smallest ADS you can have with NSNS flux. And it of course is also the dual to the symmetric product orbifold at that point. The spectra match exactly. And the symmetric product orbifold is sort of where there is higher spin symmetry and so on. So I think it is the analog of what you would think of as the tensionless limit, because it is the symmetry restored phase, if you wish. And I think there's something similar here, because it's again at the same level, but in the Kazama-Suzuki model, the SL2R module 1, the SL2R is also at level 1, which is very important for this sort of property that I was mentioning, that you get precisely these that the spectrally flowed operators get, the correlators get contribution only from very special branch coverings. I think that's very, the K equals to 1. Yeah, that's why what your analysis with 1 of the K greater than 1, there's a sort of a loophole in that at K equals to 1. There is an extra solution to the Ward identities, which correspond to, instead of singularities, you get delta functions, which are localized on those points which admit holomorphic covering.
Thank you.
A very nice talk. I had a broad question. One of the things we've learned in recent revisitations of random matrix models is that it's useful to remember that they're models of random matrices. And we tend to love to look for regimes where discussing it in terms of the Tooth expansion and strings and things like that. But we learned a lot from the other perspective that, these spectra, which characterize in certain ways. And so I've been wondering what we might learn by going back now to where you've gone, to where we first used to do random matrices. So are there any insights, perhaps from non-conceptive studies you've looked at, that might sort of see where some of that characteristic of matrices belongs in this stringy context?
Yeah, no, it's an excellent question. I've thought a little about it. They seem at first sight to be, I mean, it's the same tool you're using, but for a very different reason or a very different interpretation. So I'm not talking about level statistics or anything here.
It's there.
It's there, of course. But here, so this is the more conventional top limit, and but there may be some, I don't have anything useful to say.
If I remember right, there is another place for Gaussian matrix model in ADS-CFT, which is this circular Wilson loop.
Yes, I think that's the same. I think it's the same subsector, but for instead of trace M to the L, it's trace E to the M. So it's a sort of so that's a class of operators I haven't looked at, but I think it's the same supersymmetric localization.
Right, yeah, that was actually Brooker Gross.
Yes, right. Exactly. So those are, you can consider them. I haven't looked at them here, but you can look at trace E to the M operators, and those would, I think, correspond to those loops.
I have a question, maybe too technical, but you were saying that you insert these operators into the X, and then the momentum is conserved. But in this type of expansions, normally you get some infinitive from but when the momentum is conserved, you get some infinitive.
In the S matrix, you mean the delta overall delta function? And no, but here it's a discrete momentum. Yeah, it's a discrete momentum. Self-dual radius.
Okay, let's thank Rajesh again.